In the next problem, we have this function defined by f of x is sine cubed of x plus sine cubed of absolute value of x. And we want to find f prime of x, the derivative, when x is greater than 0 and when x is less than 0. So to do this, we really need to set up a piecewise function. And so recalling that the absolute value of x is just x when x is greater than or equal to 0, and it's negative x whenever x is less than or equal to 0, or in this case for x less than 0. Alright, so we can simplify that up a little bit because sine is an odd function, so the sine of negative x is the same as negative sine of x. And since we're cubing that function, it's going to stay negative sine cubed of x. Let's simplify the top first. Now we have 2 sine cubed of x whenever x is greater than or equal to 0. And we're going to use the fact that sine of negative x is equal to negative sine of x. And when we do that and cube that function, we're still going to end up with negative sine cubed of x. When we add that to sine cubed of x, we're going to get 0. So now we're at the point where we have the two different functions for x greater than 0 and for x less than 0. And we can go ahead and find the derivatives. We're going to find the derivative of 2 sine cubed of x using the chain rule. We bring down the 3, we take the derivative of the outside function, which is something cubed. So we bring down the 3 and reduce the exponent to 2, so now we have 6 sine square of x. And we need to multiply that by the derivative of sine of x, which is cosine of x. And that's it. We can stop at that point. And the derivative of, and that is whenever x is greater than or equal to 0. And the derivative of 0 is still 0. And so that gives us the top branch is the answer to part A, and the bottom branch is the answer to part B. For part B, what we need to do is determine whether the function f of x is continuous at x equals 0. And for continuity, remember, we need to see that the limit from the left has to equal the limit from the right at x equals 0. Technically, we still need to test the value at 0. And so those three things should be equal. F of 0 should equal the limit from the right as x approaches 0 of f of x is equal to the limit as x approaches 0 from the left of f of x. And for the limit as we approach from the left, we're going to go to the bottom branch of the original function. And so that would be just 0, right? If we used the simplified version of the lower branch, or the branch when x is less than 0, that's just 0. And we want to see if that's equal to the limit as we approach x, as x approaches 0 from the right, or the upper branch. And plugging in x equals 0 into sine of x does give 0, and 2 times 0 and 0 cubed is 0, and 2 times 0 is still 0. So here we were using the upper branch, or the branch when x is greater than or equal to 0 of 2 sine cubed of x. And so that is still 0. And so yes, it is continuous. And justification would be, now I guess what we've written there is a justification. And I might just want to add at the top of that, continuous if limit as x approaches 0 from the left of f of x equals limit as x approaches 0 from the right of f of x is equal to f of 0. And we've shown that that's true. So yes, it is continuous, and we have justified. Finally, for part D, we want to determine if the derivative exists at 0. And that derivative will exist if the derivative as we approach x, as x approaches 0 from the left. And so now we're using the derivative function, actually we're using the lower branch of the derivative function, so that's 0. And we need to show that that will be equal to the limit as x approaches 0 from the right of f prime of x, or using the top branch of the derivative function above. And plugging in x equals 0, we will indeed get 0 again. And it exists because they're both equal to 0.